Every week brings a new leaderboard. Researchers and tech companies constantly release models, all chasing the exact same title, state of the art. It is the ultimate currency of success in the AI industry. Almost without fail, that title is justified by pointing to one number. A single definitive average score across a benchmark test is broadcasted to the public as absolute proof of a model's superiority. But a recent study by Roque and colleagues on time series forecasting breaks the math behind those claims. They examined how those averages are built, and their results show that single-score leaderboards are largely a mirage. Look at this diagram of competing forecasting models. The researchers found that if you let them pick just 3 specific datasets for the benchmark test, they could make more than half of these models jump straight to first place. Even if you expand the selection to 6 datasets, the math holds. 77% of the models can be neatly placed in the top 3. There is no data fabrication happening here. The researchers didn't use any unusual tuning tricks. You simply choose the tests where a specific model performs well, and you leave out the tests where it struggles. When the winner of a leaderboard can be decided entirely by which data files you choose to include, a mean score loses its value. It hides the reality of a model's actual predictive capability. Unlike computer vision, which relies on massive universal benchmarks like ImageNet, forecasting is highly sensitive to small shifts. The dataset itself essentially acts as a hidden component of the model's architecture. A benchmark contains dozens of invisible levers. A researcher decides whether to use familiar files like weather or electricity. They set the forecast horizon. They determine exactly how much historical data to include. Every choice changes the question being asked. To see exactly what happens when those invisible levers shift, consider a well-known forecasting model called Informer. This tracks Informer's ranking across different tests. Depending on the data chosen, its position bounces violently from first place down to 13th. Compare that to classical methods like ARIMA. Despite seeming outdated, these models maintain highly stable positions near the top, regardless of data filters. A single mean score only tells you what happened after all those convenient choices were locked in. The headline number masks massive underlying volatility, making it incredibly easy to publish an unfair comparison. Almost none of this is driven by fraud or intentional deception by individual researchers. The issue is a systemic feedback loop. The scientific field tends to reuse the exact same 6 datasets for publication. That means new architectures are continuously proposed, tested, discarded, and revised against a fixed sample. Over time, this collective behavior ultimately causes the entire forecasting discipline to slowly stop measuring generalized predictive skill. The work that looks good on those specific files is the work that gets published. This benchmark loop accidentally transforms what should be a test of real-world capability into a meaningless measure of historical overfitting. Fixing this does not require tearing down researchers with suspicion. It requires a structural shift in how peers and the public demand data be reported. Instead of a deceptive average score, look at a rank distribution. Here, a single mean dot expands into a horizontal box plot, revealing the hidden spread of data. If this box plot is wide, the claim is fragile, highly sensitive to dataset manipulation. But if the box plot is narrow, the model has genuine, robust support across multiple varied tasks. You can use a practical checklist to evaluate future AI claims. First, count the datasets. If a paper reports 6 datasets or fewer, treat its ranking as a single random draw from a much larger distribution you haven't seen. Second, look for absolute errors rather than relative percentages. A 20% improvement is incomplete without knowing the underlying score. Finally, check if the baseline model was given the exact same tuning budget as the winner. A heavily tuned proposal beating a default baseline is a common, invisible asymmetry in these tests. The next time a model claims to be state-of-the-art, the first question must never be, how much better? The first question is, on what data, compared to what, and how many other stories would 3 different files have told?